Hello, my name is Miranda Cravetz. I am a first-year PhD student at Oregon State University, and my advisor is Joe Davidson. Today I will be talking about state estimation of an underactuated gripper during robotic fruit picking. My work at the moment centers on selective robotic fruit picking, and that lets me contribute to two interesting problems. The first is the divide in agriculture between efficient land use and efficient labor use. To maintain dense plantings of crops and to ensure that no crops are left behind during harvest, producers generally need to care for the crops with diligent manual labor. Industrial techniques, on the other hand, require much less worker power, but there must be enough open space to accommodate large machinery, and some crops are left behind or damaged during the harvest. Robotic harvesting has the potential to bridge this gap by using smaller, more intelligent machines that work more like humans. The other problem is the divide in robotics between computational intelligence and mechanical intelligence. We tend to see two distinct approaches for robotic grasping. One is getting a robot to perform incredible grasping tasks under controlled conditions using fully actuated, highly sensorized systems that are well suited to being controlled. The other approach is developing hardware with mechanical intelligence that is robust enough to be practical in unstructured environments. These generally have fewer actuators and degrees of freedom, making them difficult to control, and often contain compliant components that are incompatible with traditional sensors. Robotic fruit picking requires both the computational intelligence to carry out sophisticated picking tasks and the mechanical intelligence to operate in cluttered outdoor environments. So the question is, how do we bridge this gap? And the answer is, we don't know yet. But we did take a robot outside and try to pick apples. Here you can see a robotic gripper developed in our lab which has 3 tendon-driven fingers positioned radially around a soft palm. The design is based on the Yale Open Hand, with modifications that make it more optimized for apple picking. This past summer, we put the gripper on a UR5 manipulator and performed picking attempts on a Honeycrisp apple tree. You can see one of these attempts in the video on the right. In this case, the apple slips out of the hand because during the initial grasp, the hand has grasped both the apple and the branch. Obstructions such as this were a common failure mode during field trials, since there are so many obstacles close to the apple. We decided this was a good place to start looking for solutions. We decided to ask, can we replan a grasp if the gripper encounters an obstruction? We realized that any method to evaluate whether a grasp was obstructed would need to know the pose of the hand. However, this is non-trivial since the hand is underactuated. It is impossible to know just from the state of the motors what the pose of the hand is. Our proposed solution is to sense the pose directly with inertial measurement units mounted on each link of each finger. To validate our approach, we used 2 of our flexure-based fingers to create a planar gripper, and created a test bed to test our solution in 2-dimensional space. We decided to model the gripper as though it had a rotational joint located in the center of the flexure when the hand is in its resting position. We then find the joint angles using the inertial measurement units, and use a simple kinematic model to estimate the pose of the hand. As a ground truth, we used computer vision to track the link centers of the gripper, and compared this location to the location of the link centers in our kinematic model. At the time of submitting our abstract, we had conducted 3 grasping trials and found an average positional error of 14.2 millimeters. After some improvements, we have now conducted 14 trials with an average error of 10.9 millimeters. In all cases, the estimated pose visually resembled the pose in the real world, and we are excited about the promise that this technique holds. That being said, most of our work is ahead of us. In the near future, we need to find the current sources of error and further refine our approach. Then we need to deliver on our initial goal of detecting obstructed grasps. In the next few years, we hope to conquer more challenges than just detecting obstructed grasps by combining our technique with other new ideas. Eventually, we'd like our robots to be just as good as a human worker.